All right. Oh, we won't do quantum mechanics review. What we're going to do is what I promised here. We are going to look at oh goodness. I printed out both of the next two slides so I wouldn't have to go back and forth, and I left it in my office. We're going to look at the derivation for a wave based on Maxwell's equations. So here's Maxwell's equations in all of their glory. Again, we have the two forms, the integral form and the differential form. I'm going to go grab those papers. So I have this sheet, and then the next one, which is the way to go about deriving Maxwell's, or the wave relationship. So since we're in the calculus class, we can do a little bit better job here in terms of understanding the equations than as I read them out to the people in the 152 class. So remember, this thing here is the directional derivative. That's equal to actually, yeah, that's what you guys are using in calculus for your notations, right? Except for he doesn't put the hats on them. But so that's the directional derivative. So when you have, and I learned to call that del. So I have del dot E here, right there. That means I'm taking the derivative with respect to x, and that's the x component, or the derivative of the derivative of the x component with respect to x, plus the derivative of the y component with respect to y, plus the derivative of the z component with respect to z. And that tells us rho here is the charge, and epsilon 0 is that constant, the permittivity of free space. So fundamentally, you can determine the charge enclosed. Now, rho, I said charge, it's charge density, charge per unit volume. So this would allow you to find the charge density based on the electric field, or as we had on that homework, the calculus-based homework assignment, you found the charge density based on the electric field. Actually, yeah, I said or. That's exactly what you found, was the charge density based on the electric field, right? So that's the differential form. The integral form is the one that we actually studied. We have the charge enclosed, and here it shows specifically integral of the charge density dV. The epsilon 0 is a constant. It could be outside of the integral. The charge enclosed over epsilon 0 is equal to the flux over the closed surface. Then the magnetic one, it looks exactly the same on the left-hand side as the electric one. But it's equal to 0 on the right-hand side because there is no magnetic monopole. That means your magnetic, no matter what your volume, the magnetic charge enclosed is always 0. So that's why it's equal to 0. Yes?
Is there actually no monomagnetic
I'm with
pole?
You.
Or is that just one of those things that we just say because we don't experience it?
Okay, so Trace's question is actually a super valid question. Super valid. That's just valid. We know of no reason why it should not exist.
We just haven't.
We have never discovered one. And I think it's Alan Guth, the guy who came up with the idea of the inflationary model for the Big Bang. He's a particle physicist. He's not a cosmologist. He got to that idea because he was studying magnetic monopoles and calculating how much energy it would take to make a magnetic monopole. And he came up with his book. Like I said, I think I've said this to you guys before. It's pretty funny. He says it has to make a particle accelerator that extends, so far out of the Milky Way galaxy in order to have enough energy to create a magnetic monopole. And the federal government, for some reason, wouldn't fund that. A little fun. And so that's what got him interested in cosmology. And according to his calculations, the Big Bang would have enough energy to make maybe 7 magnetic monopoles. So according to Guth, there might be 7 magnetic monopoles distributed throughout the universe. And we just haven't been lucky enough to find one yet. So the answer to your question, it's something that's been studied a lot. And the present understanding is it could exist, but it's not known to exist, and we don't expect to ever find one. Doesn't mean we won't ever find one. So, I think our textbook just says there is no magnetic monopole. But you should be a little more wishy-washy on it. We don't know of any to exist. Then the last two are a little more complicated. Once again, notice the left-hand sides are the same. This del cross E is called the curl. So this here would be read the curl of the electric field is equal to minus the rate at which the magnetic field is changing. And the curl of the magnetic field is equal to this here times the rate at which the electric field is changing plus the J is the current density. Yeah, Mike.
Is that just a fancy way of saying cross product?
Well, the curl is del cross. So curl is a fancy way of saying del cross, not just cross. It has some useful things, like one way to test if a force is conservative is if the curl is 0. If del cross F is 0, then it's a conservative force. So it has some useful mathematical, useful enough to get its own name. So those are the equations. And of course, you don't have to have these equations memorized. And the important thing that I pointed out, especially if we're talking about electromagnetic waves, is that we have a changing magnetic field will produce an electric field, and a change in electric field will produce a magnetic field. And so it's that basis that allows us to support electromagnetic waves. So here is the list of steps to go through and do the work that Maxwell did to show that these equations will give you an electromagnetic wave. So I'll read these steps. I'm going to go back to the previous slide and work my way through doing the derivation. So first you take the curl of both sides of the differential form of Faraday's law. You could have started doing it with, there's more than one way to skin this cat, and I just chose one of them. Use the vector identity that del cross E is equal to del times del dot E minus del dot del E. How many people knew that identity? Yeah, me either. And then we'll substitute the differential form of Gauss's law for a vacuum. For a vacuum. So what we're doing here is specific. We're saying that for Maxwell's equations will predict an electromagnetic wave in a vacuum because we're doing our derivation specifically for that case. It would work for other cases, but we're doing the simplest one for a vacuum. So in a vacuum, the charge density is 0 and the current density is 0. Right? You don't have any charge floating around if a vacuum means nothing there. And you're not going to have any moving charge, current density, if there's nothing there. And then finally, we substitute the differential form of Ampere's law into the right side of Faraday's law. Boom. So let's do it. 8. So starting off, and of course, I've got to use my cheat sheet because I'm not going to remember. It has the same thing you just saw. So I'm going to start by taking the curl of both sides of the differential form of Faraday's law. So here's Faraday's law, differential form. So step 1 is to take this and take the curl of both sides. So I'm going to have so there's the curl of the left side. There's the curl of the right side. Now, the del operator is independent of time. So I can move that through a derivative. So I can rewrite the right side as minus d dt of del cross B. Right? Does that make logical sense there? I move the derivative with respect to time outside of the del cross because the gradient operator only depends on spatial coordinates, not on time coordinates, and that's a partial derivative. Now, we can see right away del cross B, we'll be able to substitute this in there. That's the last step, I think, in my, that's the last step in my process. So I'm not going to do it yet, but we can see where that's going to go. Focusing on the other side of the equation, actually, I'm going to set my equations to have different colors for different sides. So focusing on the left side again, we have del cross E, and we're going to use the definition that del cross E is equal to. And so this is definition that none of us have memorized. Probably none of us have ever seen this before. Well, none of us. I have. You guys haven't. So I only did one step there, and that is the substitution. Well, del dot E, I can now do a substitution for del dot E. That is del dot E is the charge density over epsilon 0. In a vacuum, what's the charge density? Go ahead. It's 0, right? If you're in a vacuum, you have nothing. Hence, there's no charge. And so in a vacuum, we have that's 0. And so we're left with minus del dot del is written as just del squared. It's a scalar when you do a dot product. So del squared E. That is a spatial second derivative. And then the other side equals, and now I'm going to substitute for the del cross B. Don't forget the ddt, minus ddt of, and using my substitution, mu naught epsilon dE dt plus mu naught times 0 in a vacuum and so now I have a minus sign on both sides of my equality. So I'm going to multiply everything by -1 just to get rid of that. And I have del squared E. And actually, I dropped a vector sign. That should have had the vector sign above it. Is equal to mu naught epsilon naught second derivative because it had ddt of ddt. Or as we usually write this, actually, no, that is how we usually write it. What am I saying? Now, does that mean anything to you? Maybe, maybe not. First semester, when we talked about waves, we did have this equation, but I don't think we did anything significant. I usually do a lecture where I go through and derive why this wave equation exists. But this is the definition of a wave equation. You have the second spatial derivative of your displacement equals 1 over speed squared. So in general, del squared F equals 1 over c squared, second spatial derivative with respect to time, that's the general equation for a wave equation. And so when James Clerk Maxwell did this and gets to this result, he's like, hey, this supports a wave with electric field as the displacement. So the electric field is oscillating electromagnetic wave. Now I said electromagnetic. I said electric oscillating for electromagnetic. If we were to come back and do this by starting with the Gauss Law equation, well, actually, if you start with the Gauss Law equation, you have yourself a bit of a problem because you have 0 on the right-hand side right off the get-go. But I'm trying to think of what the other method is to start this. It must be starting with Ampere's law. But if you go through the process, you can also end up with this same relationship in terms of magnetic field B. And so you have an electromagnetic wave with both electric and magnetic fields oscillating. So now on the test, you will not have to regurgitate this. And then you might ask, why do you spend our time on this if it's not going to be tested? Of course, the answer is, I want you to learn things, but I also recognize that you won't be able to, you'd have to just memorize it if you were going to put this on the test. That's not real learning, at least not in the way we're looking for in physics. But what I want you to see is that, yes, there is a nice logical pathway, something that you can understand. The only thing here that is outside of your present scope of understanding is this vector identity right here. And proving that it's straightforward, it's a grind. That's the only thing that's outside of your current capabilities. And like I said, you can do it, it's just a grind. But I want you to see that, yes, they do indeed predict this equation, which is the equation for a wave. Now, I'm not done with today's lecture. I'm going to review for the test. But that is the new material for today's lecture. Just seeing how we get the wave equation. Does everybody understand why this is important? Going with that's a no. Without this work, we would not have had that leap in logic to say that light is an electromagnetic wave. And so our understanding of light made a big jump forward at this point when he said, wow, this gives us a speed that's the same as light. Light must be an electromagnetic wave. Not a very good logical jump, but then people stayed and found out, sure enough, light is an electromagnetic wave. And so everything that we knew about light, and we knew a lot, we humanity, knew a lot about light at this point, because light's something you see every day. Electricity, magnetism is not something that you can see and interact with in the same way that you can interact and see light. And so the understanding of electricity and magnetism was way behind the understanding of optics. And so all of a sudden we suddenly have a much better understanding of what's going on behind the scenes for the optics. So it's a very significant step forward. Now let's go ahead and does anyone have any questions before I go on to review? Okay, then let's go ahead to review. So what kinds of things could you see on your one problem that's going to be a calculus-based question on the exam a week from today? Not a week from today, 2 weeks from today, Trace. Trace corrected me on that yesterday. And so here I have the 4 things that would be stuff that might show up. Notice the Faraday or the Maxwell's equations derivation is not here. So you have transient circuits, both RC and RL. Ampere's law, Biot-Savart law, and Faraday's law of induction. So before I go to look at these, I think I have like one slide for each. What is Ampere's law?
Are you asking the equation or what it?
Let's go with what it fundamentally means. What does Ampere's law tell us? A blank creates a blank.
Magnetic field creates a charge.
Does a loop create a magnetic crazy current?
We haven't gotten there yet, so it's good that I asked this question. We have the right ideas blowing around here, but not put together in the right order. Ampere's law says that a current will create a magnetic field. So Ampere's law, a current makes a magnetic field, and what we have for our calculus form is actually, it was shown here, whoops, right there. The form that you would use is this form here. Except for, we learned it without this initially, right? This is the part that Maxwell added in for an electric field, and we're not going to apply this for a change in electric field. And so this integral of j dot dA is just, oh, snap. I am missing a mu. There, all better. I was missing that mu aught in my equation. It's kind of important. So the form that you learned is just the integral of b dot dl is equal to mu aught times the current. Right, the dE dt stuff was 0 for what we're going to do, and integral of j dot dA is just current. So, that's not where I started here. Here is the form, so I'll just cross through that because that's not what you're going to use, of what you would use if I give you an Ampere's law problem. Now, if we're going to utilize this, this is like Gauss's law. We need to have the appropriate symmetry to make this simple. If we don't have appropriate symmetry, it's kind of rough. So in the end, we didn't do any calculus with this equation. I don't think. We used symmetry arguments to do it without calculus. So do you remember what cases we applied this to? A wire. A wire was it's the gold standard of where we apply this. If I have a wire with current going through it, then I say, okay, that circulation, the integral over closed loop of b dot dl. What loop can I make where that integral is easy? And based on the symmetry here and the fact that magnetic field lines always form closed paths, the only symmetrical shape that the magnetic field lines could have here would be a circle around the wire, concentric with the wire. And so we say, based on the symmetry, I'm going to have to use a circular path to do my calculation. So I use a circle. So magnetic field is parallel to dl at all points on that circle. And B is constant. Well, can't put the vector sign. B magnitude is constant along circle. So this writing in red is the symmetry argument for us to do this. So here's my loop with radius r. And now that I've decided that the circular loop is what I'm going to use, then I do the two sides of my equation independently. So what's the other side of the equation? Mu naught I. So the black part, the integral of b dot dl, since b is parallel to dl, what does that tell us about the integral of b dot dl? Just the parallel part. Yes, it tells us that the dot product is just b times dl, because remember, a dot product is always a vector dot b vector is equal to ab times cosine of the angle between the two. So if the angle between the two is always 0, cosine of 0 is 1, and so that's just b times dl times 1. And then going further, if b is constant, what can I do with b in the integral? Just move it outside. But then I have the integral of dl. By definition, what's the integral of dl? L. And since this is a circle, L is 2 pi r. So now we have the integral done without ever actually doing calculus. Now you had to know the integral of a constant is, constant can come out of the integral of dl is L. So there was some calculus requirement there, but there was no actual, I better look up at a table, or I don't know how to do this integral. It was very straightforward. So there we've done the left side of the equality. Now we shift to the right side of the equality. How much charge is enclosed, or how much current is enclosed in this loop? There's only one wire. The wire carries I, so how much current is enclosed? It's not a tough question, friends. It's the obvious answer. Yeah, how much current is enclosed by my blue loop? I'm waiting for an answer just because I want to make sure people understand the equation. It's not 0 because there's a wire carrying current going through the loop. It's just I, right. Right. I want to make sure people actually make that recognition instead of I'm not sure where that came from. If I had two wires, one going up and one going down, both carrying I, what would the current have been? If one's going up and one's going down, it adds to 0. So we just have to calculate how much current is going through. So now that we have that all done, we just set the integral of b dot dl is equal to b 2 pi r is equal to mu naught times current through, and therefore the magnetic field is equal to mu naught I over 2 pi r. So that's how we use Ampere's law, or Ampere's law. Now that's the first and the most significant usage we have. What other usage did we use for Ampere's law? Where else did we use it? Okay, we did it on a solenoid where we have a lot of loops. And then we had to be a little trickier because just like using Gauss's law, you want to have some symmetry arguments like we had here. And so for that solenoid, we chose a rectangle with one part of the rectangle going through the center of my coil, two sides that are perpendicular to that, and then very far away, a last side that's parallel. And the reason for this shape is, based on symmetry, if we're at the center of our solenoid, the magnetic field lines are all going to be moving in the direction of the axis of the solenoid. So if the solenoid is line, I should go back a page, well, 2 pages. I'm going to do it here. If I have a solenoid that's like this, okay, so those are, I drew an inductor because that's what a solenoid is, really, same thing. We make a loop that goes like this so that the magnetic field lines are going to be going like that. So the magnetic field is parallel to the wire that's in the middle of the solenoid, perpendicular to the sides of the wires. And then if we make this long enough, B is approximately 0 if we get long distance away. And so in that case, let me call it A. Okay, I put the 2 plus zeros for the sides because of perpendicular. And then A times 0 because the magnetic field is approximately 0 out at the end. And so that circulation is a simple result without having to do any calculus again. And then we have to have how much current is enclosed here. And this is not as easy as the last one, because I have a bunch of loops, and if I have A is larger, I'm going to have more loops enclosed and hence more current. So the current enclosed is going to be equal to the number of loops enclosed times the current. So it's the current times the number of loops enclosed. And to determine that number of loops enclosed, we said, well, if I have lowercase n is equal to the total number of loops divided by the total length, then the number of loops enclosed will be equal to the length of my A, the width of my little box, times n. And so that's equal to IAN. Right, so the reason I waited for you to answer on the last one is because this one here, you have to have a solid understanding of what that current is to be able to see how we got there. And then we put these together then. The circulation is A times B inside is equal to mu naught times the current that's enclosed, so IAN, divide both sides by A, and you have the magnetic field inside the solenoid is mu naught I times the number of turns divided by the total length. So that was the second application of Ampere's law. So if you're going to have something with Ampere's law, it's going to be one of those two. And you would need to have the ideas there, the ideas on why you chose the shape for your loop and how that made your calculus simple. Is that clear? Okay, then the Biot-Savart law. The Biot-Savart law is like Coulomb's law. If we don't have a simple geometry, then we have to use the Biot-Savart law. It's still the same idea of Ampere's law, that a current is going to create a magnetic field. But now we have that cross product equation here, that dB is equal to mu naught over 4 pi. That's a constant. That we don't have to worry about too much. Current ds now is the path the wire's taking, cross r hat, I'll take the top one, r hat is the unit vector pointing from the piece of wire where ds is to the point where I'm finding the magnetic field, and then divided by r squared. Now that's more complicated. We were able to use this to do things like to recapitulate what we found with Ampere's law. That is, the first case we used this on was, we said, let's take a straight wire carrying current I, and we have some point out here P, and we want to find the magnetic field there. And so you have to define, well, here's my little piece, and I'm going, here's ds vectors going like that. My r vector is like that. And so you use the right-hand rule to find the direction. So ds, index finger, then orient your hand so you can go bend to r vector, and thumb points in. So at this point, and notice it doesn't matter where on the wire I am here, I'm still going to have going into my page. So the first thing I identify is the direction. If I have more than one direction, then I'm going to have to break things into components, just like we did with with Coulomb's law. Oh, Gauss Law too. Then I need to actually find what ds cross r is. In this case, it was easy. If this distance is a, is a, then the perpendicular part of the r vector is a. So I actually solved it using this form, because for my case here, ds cross r vector is equal to ads, where I've dropped the vector signs. Well, I'll put in here so it still has the direction. It's a times ds. That was easy for this case. And then I have mu naught over 4 pi. That's constant, but r squared. How does r change with ds? Obviously, r is going to be different depending on what your position s is. So you have r is equal to, well, r squared. No, we'll stay with r. R is equal to the square root of s squared plus a squared. And so you can either put that r in, then you have the whole equation. It has s as the only variable and integrate over your limits on s, or you could use a trig substitution with an angle. And then you would be able to find and verify that what we found with Ampere's law is the same thing as what we find with the Biot-Savart law. Another case where we used the Biot-Savart law was a circle, a current circle like this. And the way we did it is we did for a point that is along the axis coming out of the circle. So our symmetry is nice and easy. And then we found the magnetic field produced at some point in that axis. So you should be able to do either of those variations with the Biot-Savart law. So I'm not going to continue the first one or redo the other one, because we only have 10 minutes left. I just realized I can't just redo everything. So that's what you need to know about the Biot-Savart law. Faraday's law of induction. This is really the most recent of the four things. Faraday's law of induction says a changing magnetic flux produces an induced EMF. So you need to be able to calculate the magnetic flux. Integral of B dot dA. So, be able to calculate that flux. We've already done electric fluxes probably to death. And so now you're just doing a magnetic flux, same calculation in essence. But then we have the time derivative. So then the next step is the derivative of this with respect to time. So since that, and I probably won't give you any case where you actually have to do the calculus here. It'll probably be, something with a fixed area, so you just have B dot A. But you have three things that can change if you have flux is B dot A. What are the three things that could change if flux is B dot A? How do we write B dot A as a scalar product? Dot products, it's always, the result is, it's scalar. And if it's B dot A, what's it going to be? B times A times cosine of the angle between the two. So if I have B is like this and A is like this, theta is the angle between the two. So I have three things that could change, B, A, and theta. And so what you would fundamentally have to do if I give you a problem with Faraday's law of induction is you'd have to take the derivative of dA cosine theta. And you could have theta changing, you could have A changing, you could have B changing, you could have all of them changing. What do you do if they're all changing? Well, you have the product rule, which is fundamentally doing it three times, yes. So you apply the product rule if you have more than one changing. And so that's what you'd have to do with Faraday's law of induction if that's what comes up. Now, the last thing that could come up, the one that I had listed here first, was transients. Transient circuits are circuits that are changing from state A to state B. And you could have either an RL circuit, a circuit that is and I'm just going to make this a rather naive circuit, a circuit where you have a switch that can close and you change from one state to another with a resistor and an inductor, or you would have an RC circuit. If it is containing an inductor, then you're going to use that relationship. The voltage drop across inductor is equal to the inductance times the derivative of the current through the inductor with respect to time. If you have a capacitor, you're going to instead use this relationship. And then you use Kirchhoff's laws to create an appropriate equation. So as an example, for this equation right here, or for this circuit right here, I could say okay, guys, VL is L di dt. I have an equation like that. And so what would I do with an equation like that? This is a differential equation, right? Differential equation because we have a derivative in it. and I'd want to solve for I. So the first thing I have to do is separate variables. So I'm going to take this equation and first put the derivative on one side. And divide everything by L so the derivative is by itself. Now, I don't have my variables separated. I have i's on both sides of the equal sign. I can't, well, first thing I would do is sides by dt to get side. If I multiply both sides by dt, then I have di is equal to this. I still have i's on both sides. The only way to get I away from this side is to divide the entire thing that's in parentheses. So the next step is so I have that relationship. I dropped a minus sign somewhere. It's important. So now I can integrate the two sides independently. The right side, integrate from time initial equals 0 to time final. So that's equal. That's easy. That's just time final. The left side, well, the way I learned to do these things is I always use a U substitution. I let U equal E over L minus I R over L. So du is equal to minus R over L di. Therefore, di is equal to minus L over R du. And this integral becomes minus L over R from U initial to U final, where U initial is going to be E over L minus I initial R over L U final instead of I initial I final. Well, if you do that, you have that relationship. Whoops. So U final is going to be initial so I have that relationship. Next to last step, what's the inverse function of natural log? E, the exponential. So I do the exponential on both, well, move the L over R across. So I don't have space to write, and I'm out of time. You would have minus R over L time final. Take the exponential e to the minus R over L time final is equal to the stuff that's in brackets on the right-hand side, and then you solve for I. And so that's the process that you would go through for the transient circuit if I were to give you one. Now, I only did the case of a resistor and an inductor because we did the case of resistor and capacitor. So between the things we did in class today, what you're going to have on the test will be one of those things. Any questions?
This slide will be online.
Yes. Yeah. Any other questions? All right, then. I'll see you for lab today.